the 19th century. So he studied a lot of analytic properties of such functions. Look at that, and I will use this representation to simplify my expression for pressure and the N over. But before, let me to mention here that this function, which introduced it just recently to the, reintroduced it recently to the community, have very important, some important properties. One of the important things, fact, is that if you just play with the parameter here, the C, so this C is our C, just maybe rescale it that. And if you set Z1, you see the Z1, what is the Z1? Is exactly the critical point, yeah? I told you, the N over V will be infinity when Z is 1. When you set Z1, so this function reduced to the zeta function. So from this slide, you will understand, like me, that the Bose-Einstein condensation is related to the zeta functions. And generalized Bose-Einstein condensation, the model which I proposed, is related to the Lerch zeta function. So actually, we find the physics for the Lerch function. Lerch function appears as a condensation in the condensation parameter of some kind of the modified Bose-Einstein system. So using the Lerch function, you can simplify the expressions. I want to pass from this slide very quickly. So equation 9 and 10 gives you the number of the particle and the pressure in terms of these new functions. And it's interesting that if you take the Z very, very smaller than 1, you can get explicitly the equation of the state. And that will be the equation of the state of this type of the matter. And you can develop the thermodynamic here, but I didn't develop thermodynamics. So I mean, you can find the entropy and even Gibbs energy and study the type of the phase transition of something. But actually, thermodynamic is not my interest. So I pass to see that is it really possible to have the Bose-Einstein condensation here or no? It is just formal calculation. So we're back to the equation, which from this equation you see that this is the density of the part and the number of the particles in the ground state, and V is the volume. And this lowercase v is called a specific volume, as we know. Thanks to the system as a bosonic system, the Z, the fugacity changed from Z to 1, and this parameter C, which I introduced in my original model, so it's in the range of the real numbers. So these functions, these Lerch functions, is bond positive, monotonically increasing single value function of the Z. These four terms, bond positive, monotonically increasing, and a single value, guarantee for me that it's possible to have this inequality. And this equality can be translated to the equivalent form that the Bose-Einstein state is the state that the thermal wavelength becomes larger than the distance between the atoms. And this is they call it Bose-Einstein condensation. So the quantum effect becomes important because the thermal wavelength becomes bigger, even bigger than the distance between the particles. Anyway, if you wanted to back to and to see that is it possible to find the critical temperature, you needed to just set Z equal to 1 and these new functions. If you set at Z equal to 1, you will see that these functions will have an upper bound. It will be given by that, and because of the C is a real number, so it will be less than the normal zeta function. So the scenario which happened for the condensation for the zeta function, it repeated here. But the bond for the temperature will be different from the bond of the normal Bose-Einstein condensation. So what is the critical temperature? Actually, our situation is very hot. So to find the critical temperature, you needed to solve the equation. This equation cannot be solved analytically. But anyway, if you just pass the very low temperatures, So you can solve that by approximation, and that gives you the expression for the critical temperature. What is the M? M is the mass of this boson, yeah? Because of this equation and because of the mathematics which exist for this function, you can see that here the critical temperature will be proportional to this square, and this square root gives you a lower bound and the mass of the boson, yeah? So we are able to estimate the mass of this type of the boson, in this atypical Bose-Einstein condensation. And we are lucky that in the appropriate units, you can say that this bond is allowable from the mass of the boson Higgs. So if you wanted to find the order of the phase transition, or if you wanted to really go and define the density of the number of I call it density because it is n over v. If you wanted to find the density of the particle at the ground state, you needed to find this exponent. So this exponent is the critical exponent. But to find the critical exponent, you need a numerical simulation. So in calculation, I don't do that. I wanted to go and explain that which kind of the boson you have here. Is it different things? Is it different boson or no? The statistical boson or no? So I need to back to the density of the state. So the density of the state defined as a relation between the ratio of the volume, as you know in the statistical physics. So this factor G is the degree of the freedom or degeneracy. So VAP is the volume in the phase space, in the momentum space. This is a configuration space, and this VQP is the volume in the phase space. So, you know, we started by some kind of the density of the state. So if you use my density of the state, I propose that form, and make this integration, you find this dispersion relation for the system. So it gives you the energy versus the momentum. So it doesn't look like relativistic or autorealistic or something. It's a completely new type of the energy distribution relations. This function P log is the principal solution for this equation. From this equation, you never get idea about what is this dispersion relation. So to see that, what is the relation between the energy and momentum, I make some simplifications. For example, just think about the low momentum case, and at the low energy levels, you can just make a Taylor series from the expression, and you get this. So does it remind you something about any other dispersion relation? No. So if it was E, for example, alpha P, so we say that, okay, this is an ultra-relativistic case, yes. If it was a radical P squared plus something, we say that this is a relativistic. But this is actually completely different type of the dispersion relation. This is a non-Euler cubic dispersion relation. And if you go to the ultra-energetic particle, maybe you guess that the regime of the ultra-relativistic or ultra-energetic should be like the photon. But unfortunately, even if you pass to this high energy regime, you will see that the dispersion relation becomes very strange form. It's a logarithmic. So,
singular.
Yeah. I don't remember that any type of this kind of the dispersion relation between the momentum and energy. Maybe this is in my knowledge, actually, I didn't find anything like that. So that could be considered as a relativistic correction, but if it was P4, no? If it was P4, we can consider that as a relativistic correction to this, because relativistic correction is P4. But still, you need a P square here. There is no P square here. So this is a very strange type of the dispersion relation, actually. But this is just starting the story. So I want to tell you that this dispersion relation is more interesting. The remarkable observation is that you can have a particle which with the energy zero, but the momentum is not the zero. So what you understand from this block is that, so this particle maybe has some kind of the rest mass or vacuum energy, yeah? Because you needed to have the energy zero, but you don't have the zero momentum. So what you can understand that? It should be some kind of vacuum energy or vacuum expectation energy after some quantum fields or something like that. So, and the more strange thing is that you cannot have any physical state with the momentum less than that. So this is the boulder. So this P star, when the energy is zero exactly at that, is the boulder. So we can propose a theorem and